Hi, everybody. It's Miss Wiesen, and this is the last podcast in our chemical kinetics unit, which is Unit 5. We are about halfway on page 19, and what we're going to do to finish off this chapter is talk about something called reaction mechanisms, and then at the very end, spend a couple of minutes talking about an important concept that is bound to come up in one way, shape, or form on the test, and that is about catalysis or catalysts, okay? So let's get right into it. Reaction mechanisms. What is a reaction mechanism? Well, let me just start off by writing a generic reaction here, okay? You guys have all learned that A would be our reactants, B would be our products, and the arrow is indicating chemistry has happened. Now, the thing about writing chemical reactions is, like you see here on the page, is oftentimes we get the impression that this is happening, that this reaction is happening in one foul swoop. Well, that's not so much the case. And you're going to definitely see this in a little bit more detail in our next unit, which is covering thermodynamics and thermochemistry. And what you need to understand is that reactions oftentimes are going to happen in a series or in a sequence of multiple steps. Now, we call that a reaction mechanism. So a reaction mechanism is simply a represented series of steps that represent the bond making and the bond breaking that's occurring in any particular reaction. And more specifically, just so we can get the clarification here, a reactant, the thing we're starting with, is oftentimes going to be the thing that experiences the bond breaking, right? We're going to need to break those pre-existing bonds within those reactant molecules. And then after a series of steps, or within each step within a reaction mechanism, you're going to have a series of bonds reforming to form a new products. So in just, you guys, typically speaking, when you're making new bonds, you're forming products. And when you're breaking bonds, you're breaking down those pre-existing bonds in the reactants. Okay. Now, in order to get and understand reaction mechanisms, a couple of things apply here. One, the reaction mechanism is going to be experimentally determined. Two, it must agree with the overall stoichiometry of the balanced chemical reaction. Don't worry, you'll see an example here soon. And three, it must agree with the experimentally determined rate law. So the vocabulary of mechanisms involves this term we call elementary steps and molecularity. Now, these are terms that are describing within the reaction mechanism, and you need to know how to use these words. I'm going to go ahead and just give you the definition. So elementary steps are simply the individual steps within an entire reaction mechanism, whereas molecularity, I'm getting ready to talk about here below. And so molecularity, let me go ahead and title it here, and you should too in your notes. When we talk about molecularity, we're talking about the number of molecules that are actually participating in the chemical reaction. And for AP chemistry, you need to know three of them: the unimolecular, bimolecular, and termolecular. Now, if you, one thing I would always recommend is understanding prefixes will kind of give you a precursor to what the term means. And when many of you go to take your GRE, like a graduate entrance exam into like a master's or PhD program, there's going to be whole sections on the GRE about vocabulary. One of the quickest ways to break down and understand words you haven't seen before are by looking for prefixes and suffixes within that word, right? So unimolecular, we know, means one, bimolecular, bi, two, and ter means three. Okay. And so let's take a look. What is the molecularity that can occur within a reaction mechanism? Well, if it's unimolecular, that means that the elementary step involves one reactant molecule, and it is essentially going to collide with some type of background substance, some type of background molecule that does not have an overall arching effect in the chemical reaction or within that elementary step. But what it does is it allows that one reactant to become collisionally activated. In other words, it allows the activated complex to form. And remember, and again, we're going to learn about this in more detail, but at the beginning of the unit, we understand that if a substance or a reactant becomes activated, it is going to be thermodynamically favored, meaning the reaction is going to happen and eventually the product is going to form. Okay, and so a unimolecular reaction simply involves one reactant with a background molecule or a solvent molecule. Okay, and as a general example here in your notes, you could say A yields products, right? Where A would be our one reactant, okay? And the second type of molecularity that can occur within elementary steps is something we refer to as bimolecular. And you probably have guessed it. That simply refers to where we have two reactants and they're colliding to undergo the chemistry. And if I had to represent that in a generic reaction, we could say A plus B yields products. Okay, that could be a good representation of generic reaction where you have two reactant molecules yielding the products that will eventually form. And then in a rare case, you would have a termolecular elementary step. And this molecularity defines the collision between three reactant molecules. Again, these are rare. I don't anticipate that you'll see them in AP chemistry, but they do exist. And so if I had to write a generic reaction that would kind of represent this elementary step, it would be what I just wrote on the screen. So let's go ahead and talk a little bit more about molecularity and how it relates to the rate expression. And then in just a second, of course, we will do some practice problems. So I'm going to give you a second. You should put me on pause, and I want you to take a look at this data table here. It's identifying some examples of elementary steps. In the middle column, it's describing how we would define that molecularity. And then in the third column, it would then give rise to the type of rate expression we would see. Okay, so as we go forward, I want you to keep in the back of your mind, and this is an important concept. And again, if it's not clear right now, it should be by the end of this podcast. But when you go to write the rate expression for a chemical reaction, you guys have basically been doing that for this entire unit. It's important to note that the rate expression cannot be predicted from the overall balanced reaction. And you guys know that a balanced reaction, we add coefficients in front of the substances involved, and that gives us our stoichiometry, right? That gives us our ratio of things that need to react versus the things that are produced. And since you just learned that an overall reaction is actually broken down into a series, or if you will, a sequence of steps, you can actually identify which one of the elementary steps is the rate determining step. Okay, so let me explain a little bit more, and I'll try to hit on this over and over again. When you are given a reaction mechanism, if you are told, or if you can identify which one of the elementary steps is the slowest, okay, the slowest step, that is actually going to be the rate determining step. It is the step that will ultimately give rise to the rate expression. Okay. And again, we'll come back to this in a second, but let's take a look at this data table here and see if we can put a little bit more clarification on some of the vocabulary. Now, if these are the, given potential elementary steps, and of course, you guys, these are generic. You can see the A's and B's are just representing a generic reaction, okay? And now I want to go ahead and just clarify that in the column that says elementary step, when there is no number in front of said substance, it's implied that there's a 1, right? So you know that from first year chemistry. So keep that in the back of your mind. And let's go ahead and take a look at the first row here. If you have an elementary step that looks like this, where you basically only have one reactant that is present, you can then qualify it as being unimolecular in its molecularity. Now, one thing I want you to notice, though, is take a look at the rate expression. Now, if this was the elementary step that was the slowest in the reaction mechanism, you can now make the assumption that you could use the coefficients from that elementary step to correspond to the rate expression. So what do I mean? Well, if in the elementary step this balanced coefficient is a 1, go ahead and take a look at the rate expression. What would be the exponent up here? It would also be a 1. So in the particular circumstance that the elementary step is the rate determining step, the coefficients do correspond to the rate expression. Okay, we'll keep touching on this for clarity's sake here. Let's go to the next one. If you take a look at the second row, again, you're going to have two reactants here, A and B, in this hypothetical reaction. It's balanced. You can see the one coefficients there. And since you're dealing with two reactants here, it would be classified as a bimolecular reaction. Now, go ahead and take a look at the rate expression for this. Now, if this elementary step happened to be the slowest step or the rate determining step, you can see that the coefficients from the balanced chemical reaction in that step correspond to the rate expression. Okay, let's go ahead and try it a couple more times. Take a look at the third row in this table. This is also bimolecular because, you have two reactant molecules that are involved. Both of those reactant molecules are the same, but you can see, and of course it's bimolecular, right? Bi meaning two. Now you can see here that the rate expression corresponds to the balanced chemical reaction, the coefficients. Now don't forget, when you have A to the second power, that's the same thing as saying A concentration of A times the concentration of A, right? Okay, last one. Let's take a look at the last row here. And in this particular reaction, if this step was your slowest step, right, your rate determining step, as we say, of course it's termolecular because you're dealing with three reactant molecules here, two of A and one of B, and we all know what 2 + 1 is. It's 3. We'll go ahead and take a look at the relative rate expression at that for that elementary step. You can see that the exponents of the rate expression correspond to the coefficients of the balanced reaction for that step. So one more time, you guys, you cannot use the overall chemical reaction stoichiometry to determine the rate expression, but rather if you can determine the slowest step in the reaction mechanism, you can use that particular elementary step to determine the rate expression. Okay, so a couple of things, and you already know this from the beginning of the unit. When you're talking about rate expressions and elementary steps, there's a couple of things that will affect the rate. Okay, and you know that if you have more molecules, so if you have a higher concentration, you're going to have more collisions, and hence the rate will be faster. Also, if you've got molecules that are moving faster, so we're looking at temperature here, because temperature is directly related to the kinetic energy or the moving energy of those molecules. The more they're moving about, the more likely they're going to collide, and of course, the rate would increase, right? Okay, let's do exercise 9 and kind of put some of this together. All right. Nitrogen oxide is reduced by hydrogen to give water and nitrogen, and you can see the overall reaction is given here, all right, that I've highlighted in yellow. Now, what it's saying is they're giving us a possible reaction mechanism for this particular reaction, and it's listed below. And I think one thing that might help here is if we just say, reaction 1 or step 1, reaction 2. I'm just titling this in my notes, and if you have your notes, you should as well. So it looks like this reaction is occurring in 3 steps, okay, or 3 parts, if you will. And what it wants us to do is it wants us to determine the molecularity of each step. We need to show that the sum of these elementary steps yields the net reaction. Okay, so really quick, what you're going to notice here, and this is kind of how you do these problems. I'm going to make a note in red. You're going to need to, and you're going to see this a lot more in the next unit, but you're going to cancel similar or identical, let's say identical species on opposite sides of an equation. Okay, so again, in these 3 steps, what we're going to do is we're going to cancel identical species that are on opposite sides of an equation. It's kind of like cross-canceling, if you will. Okay. Now, really quick, if this is our overall reaction, we have to, at the end of the day, show that these 3 steps give rise to this overall reaction. Okay. And the way we're going to do that, let me clean this up a little bit here, is really quick. Let's go ahead and identify the molecularity for each step. Starting at step 1, we have 2NO. So you can see this is balanced, you guys, yields this into O2. Now, what I want you to do is take a look at the overall reaction. You do see the NO species here. It's a reactant in the overall reaction. But one of the interesting things you notice is that the product that is yielded in the first step is not a part of the overall reaction. And that's going to happen sometimes, you guys. That is what we call an intermediate. We have to identify the molecularity. And remember, you're going to do that just from the reactants. And since we've got 2NO, we're going to have 2NO nitrogen monoxide molecules smashing into each other. Would that be unimolecular, bi, or termolecular? That's right. It would be bimolecular because there are two of the NO molecules smashing into each other. Okay. And remember, that kind of gives rise to A plus A yields product for the generic reaction in the chart above. Okay. Now, here's the thing. In order to determine molecularity, you need to cancel out identical species that are on opposite sides of the reaction. So just as soon as step 1 happens, you can see here that we're producing a gas that's not a part of the overall reaction, but you can also see that very same gas is what is needed for the second step, the second elementary step. And remember, these are all elementary steps, okay, you guys? That might help with the vocabulary. Let me go ahead and just put that in my notes. Now, notice that the product of step 1 is also the reactant for step 2. Don't you agree that these are the same species on the opposite sides of the reaction? Well, they are, and those are going to cancel out, okay? And so what you're going to have then for the second elementary step is you're going to have a hydrogen, diatomic hydrogen yields these two products. Now, remember, when you're determining molecularity, you're only looking at the reactants. And since N2O2 canceled out, all I'm going to initiate this reaction with is going to be hydrogen gas. And so the second step would be unimolecular because all you have is a hydrogen molecule. Okay. And then let's go ahead and see if there's any species that are identical that will cancel. I notice here N2O. And then over here on the third elementary step, that is also the same thing that we're starting elementary step reaction number 3 with. And those two are going to actually cross cancel. Okay. And anything else? No. So again, all that is going on here is that hydrogen is going to yield these two products. And so what we're really dealing with here is a unimolecular elementary step for step 3. Now is the net reaction, as they say. So if I were to kind of draw a line underneath all of this, and I were to take all of my stuff from each elementary step on the reactant side, I would have 2NO plus 2H2, right? Do you see how I got that 2H2, 1 here and 1 here? Okay. And then I'm going to yield my arrow and write all my products down. And I can see that all of my products, the ones that are remaining, are right here. I have 1 diatomic nitrogen molecule and 2 water molecules. Now, notice what's going on here. This net reaction, what I have remaining and left over, is precisely what the overall reaction is. Okay? Hopefully that gives you a little clarification. We'll do another example here in a second. Reaction mechanisms are determined by experiment and must agree with the experimentally determined rate law. The slow step is the rate determining step. The rate of the overall reaction is limited by and is exactly equal to the combined rates of all the elementary steps up to and including the slowest step in the mechanism. A reaction intermediate is going to be something that is produced but consumed in the next intermediate step. And then in just a second, a catalyst is going to go in as a reactant. We will list it and write it in as a reactant, but it's actually going to come out unharmed as a product and does not show up in the overall final reaction. Okay, so let's go ahead and take a look at exercise 10 for some more edification. You could see here they give us a balanced chemical reaction, and they also give us the experimentally determined rate expression, or the rate law, if you will. Sometimes it's easier to say rate law than rate expression. They both mean the same thing here, right? So what it's asking, or what it's giving rather, is a potential reaction mechanism, and it's happening in 2 steps. So this one would be elementary step 1, and this one would be elementary step 2. And look at what they're giving us here. They are telling us which of the elementary steps is the fast one and which one is the slow one. And remember, that's going to be important because we learned previously that the slowest step in a reaction mechanism is indeed the rate determining step. So we could use the stoichiometry from that elementary step to determine the rate expression. But in this particular case, they already gave it to us. So in this particular case, we would confirm it and see if it actually matches. And then that's actually what the question is asking overall for exercise 10. Is this an acceptable mechanism? Okay. And that is, does it satisfy the requirements that we have been talking about? Justify your answer. Let's just go through the elementary step 1 and 2. And I can see here that this is a reactant in my overall reaction. I can also see that this one is 2 as well. I go to my products and I notice that the F is not a part of the overall reaction. And so this is going to be an intermediate and is consumed in the next elementary step. So it's cross-canceled. And right now we look like we've kind of canceled anything we possibly can. So really quick, what remains overall, right? Everything from the left side of your arrow. So we've got 2NO2 plus F2, and then yields 2NO2F. And indeed, that looks very, very good in terms of matching with the overall reaction. Look at the slow step. We know that since the slow step is the rate determining step, you could say rate equals K, and in brackets, go ahead and put your first reactant in there, NO2, and you can see here that the NO2 would have a 1 exponent, or is the order of 1, and then you would bracket the other reactant to F2. It's also 1, and those 1s are indeed coming from the coefficients in that elementary step, right? And that, again, corresponds and is matching the experimentally determined rate law. Okay, now we're going to finish this unit by talking about catalysts. Now, a lot of potential multiple points are lurking here, and catalysis is defined as an increase in the rate of a chemical reaction due to the participation of a substance called a catalyst. You've probably heard of this if you've taken biology. There are things called inorganic and organic catalysts. But unlike reagents or reactants in a chemical reaction, a catalyst is not going to be consumed. Okay, catalysts are going to function by lowering the activation energy needed for the reaction to proceed, or in this case, needed for that elementary step to proceed. Okay, and you can see here that this graph, this energy graph, indicates that. You can see the catalyzed pathway in blue here, the activation energy required or needed for the reaction to proceed is lowered. So the energy required to proceed with the reaction is lowered in the presence of a catalyst. So remember, the effect of a catalyst can vary due to the presence of other substances. Now, when you get into higher level science, you'll learn about something called inhibitors. You might even learn about something called promoters. And these are things that can work in conjunction with catalysts to either slow reactions or even increase them more.